Hi, welcome to the Calculus 3 assignment practice series. And we are in the unit multiple integrals. And today we're going to take a look at our assignment worksheets number 3 about the double integrals in polar coordinates. And we're going to do some problems in these worksheets here, okay? All right, let's go to our worksheets and see what type of the problems we're going to do today. Okay, so the first problem here is that in the region showing below, and we want to decide whether we use the polar coordinates or the rectangular coordinates, and then write it out. Okay, so then we have any arbitrary functions here. So remember we said, for the polar coordinates, if your integration region is some type of the circular pattern, then we know the polar coordinates probably is a lot easier. So for examples here, like let's take a look at the problem number 1 here, right? So this one is like 3/4 of the circle. So I think probably I can use the polar coordinates. So let's take a look. What do we do here? So then we have a f function. F function is x and y. So I know the x is r cosine theta, and the y is r sine theta. And don't forget, what do we need to put here? We need to have, we call this Jacobians here, right? And then when you do, then you can say the dr d theta. Okay, so if you do dr, that means I need to find the boundary for the r. So the radius here is what? Is from 0 to 4. Okay, so then this area, so what is the angles here? The angle here from 0 to what? 3 pi over 2, right? So this is pretty simple. So I think probably this one we are going to use, the polar. Okay, let's take a look at these numbers here. This one's here. And so because this is a triangle, it's not really in the polar, like the circular type of the integration regions. So probably the Cartesian coordinates will be easier. So if you write these lines here, this will be y equal to the 1/2 of x plus 1/2 here, all right? So now if I do if I want to do the dy dx, so that means if I integrate here, okay, so if I integrate from the y direction first, right? So what is my integrations here? I can say this is here, I have f of xy, then I do dy, then do dx. So y is from 0 all the way to where? From 1 over x plus 1/2. Then I finish the x here. X is from where to where? -1 to 1. So for this problems here, probably, the Cartesian coordinates will be a lot easier here. Okay, so now let's take a look at this ones here. I think the number 3, because this is a half circles here. So I think probably the polar will be easy. So let's see how do we write it here, right? So this is the polar. So we said f equal to the r, x equal to the r cosine theta, then the r sine theta. And then don't forget what? The Jacobians, right? Okay, then we do the dr d theta, right? So we do the dr d theta. So what is the r? The radius is 0 to 1. So it's 0 to 1. Now what is the angle? Angle is start from here all the way to here, right? So it's from where to where? So it's a pi over what? Over 2 pi here, right? Or you can from the 0 to the negative pi. If you go turn the clockwise, you can do the same thing here. Okay, so now next one's here. I like to do the number 6 here. So the number 6, this problem is very interesting. The problem asks us, so they want us to sketch the regions where is my integration regions here, and then evaluated the integrals here. After, the evaluated integral is pretty straightforward, right? So I think a sketched region, so that's the one, it's, we need to be careful here. Okay, so here, let's take a look here. This one is like R. So we integrated the R first, right? So with dRs here. So R is from 0 to the 2 sine theta. Okay, so what is the 0 to the 2 sine theta? So let's see here. So R is equal to what? 2 sine theta here, right? So if I times R both sides, so I have R squared is equal to the 2R sine theta. So what is R squared? Is X squared plus Y squared is equal to, what is the R sine theta here? That is Y, right? Okay, so this is equal to 2Y. All right, so now I change that. I can switch back. So I do like this is X squared plus Y squared minus 2Y equal to 0. Then I kind of complete the square. So this is Y minus 1 to square equal to 1. Oh, so I know this is what? This is a circle. Where is the center here? The center is 0 and the 1s, right? And what is radius here? The radius is what? It's 1s here, okay? So let's take a look. So our integration regions for this province here, this is 1, this is 2, this is 1, 1, all right? Okay, so because I know this is the center, right? So center of this circle will be here. Then the radius is 1. So, okay, so the radius is 1. So will be what look like here. So what radius? Okay, so be 1 here. So I have a, well, I hope that I can touch. Okay, so I can do a good job. So this will be my circles, right? Okay, so this is the circles here. Okay, so now I need to decide, is this is the whole circle? Let's take a look at d theta. Theta is from the 2 pi over 2 to pi. Okay, theta is from the pi over 2 to pi. Pi over 2 is the y-axis, right, to pi. So which part is my integration regions here? This half circle, right? Because this is a pi, then you swim the whole thing here. So this is a pi here. So this is my integration regions here. Okay. So after that, and then they say also evaluate this, and then this will be pretty simple, right? So here, this is r dr d theta. And then here you just say the pi over 2 to the pi. Then this is 2r squared. Then 0 to the 2 sine theta d theta. All right. And so what do we have here? So this one's here is r squared. So this is a pi over 2 to pi. So 2 theta, so this will be the 4 sine squared theta divided by 2. So this is 2 sine squared theta d theta. And then I trust you know how to integrate this ones, right? You need to use a double angle of the cosine. And like I said, calculus 3, we're not teaching you really physically how to integrate. So you can do it by yourself. And it turns out this is pi over 2 here, right? So you use double angles, right? So you just change the sine square. So this is 2. The sine square is 1/2. 1 minus cosine 2 theta, right? So now you can, okay, so this one you just change to this one. So now you'll be able to, so this is sine square, so you use the half angle formula, then you get it, all right? So this is number 6. So the interesting part is, do you know how to kind of find the integration regions here? Okay, so now let's take a look at the number 8 here. Okay, so the number 8 here, so we say the R is the region in the first quadrant enclosed by the circle x squared plus y squared and the line x equal to 0 and y equal to x. All right, so let's try to graph it first, right? So this is x, this is y, and x plus squared y squared equal to 4. So it's a circle. So it's 1, 2, 1, 2, 1, 2. Okay, so it's in the first quadrant. So that means is these quarter circles here. Okay, and the line x equal to 0, x equal to 0 is y-axis, y equal to x is this lines here. So where is my integration regions is here, right? Okay, so this is my integration regions here. And this is y equal to x, and this is x squared plus y squared equal to 4. So in here, I said, okay, now let's try to change it to the polars, right? Okay, so this one's here, this is my region R, right? So I said region R, 2x minus y dA. Okay, let's switch to the polars here. Okay, so 2x is 2. So what is the x? R cosines, right? So 2r cosine theta minus y is what? R sine what? R sine theta. And don't forget what you need to times here. You need to times the Jacobians, right? Okay, now let's take a look which one we want to integrate first. You say dr d theta. Okay, the R is, because this red region is my integration region, so it's the R is fixed. So it's from the 0 to what? From 0 to 2, see here, okay? Now my thetas here, this is my thetas, right? So this is theta. So what is the theta? Because this is y equal to x, right? Y equal to x is equally divide this 90 degrees angle. So what is my theta going to start at? Pi over what? Pi over 4. And here, all the way to the y-axis is what? Is pi over 2, see here, right? Okay, so now, in here, now we can kind of, because the R, and we can factor the R out, and so we can say here, you can, in fact, here, we can do this is pi over 4, pi over 2. You get the cosine theta minus sine theta, d theta, and this is 0 over 2. You factor, so it's r squared dr, right? So because the r and the theta, their boundaries are constants, you'll be able to factor that out. And also, so this part is just so like this part is just a simple integration, and this part is also is just a simple trig integration. And so the answers here will be like 16 over 3 minus 4 square root of the 2. Okay, so now you see we changed the integration to a quite simple ones here. Okay, now let's take a look. The next ones here. The next ones here, they said e to the x squared. D is the region bounded by the semicircle x equal to 4 minus y squared. So that means it's x squared plus y squared equal to 4, right? Bounded by this one and the y-axis. All right, so let's see which area I'm looking for here. Okay, so this is 1, 2, 1, 2, 1, 2. Because x is 4 minus y squared, so I know has to be what? Has to be on this side, right? Because it's a positive. So has to be on this side and the y-axis. So where is my integration regions here? It will be this half circle, right? Okay, so it's the reason why it's not the other half is because x here is what? X here is positive here, right? Okay, so now let's take a look. How do we change that? So I know this one also is super easy if we change it to the polo, right? This is dA. Okay, so now let's say here, so this is e, the x squared plus y squared is r squared, so it's e to r squared. Don't forget times what the Jacobians, right? Okay, so now let's take a look at dr, d theta. Okay, so the dr is pretty easy. R is the radius is 2, so it's from 0 to 2. Okay, so now let's take a look at the theta. Theta is really is from here. You can, the theta, you can treat it as from here. You can like go up, right? So from here, so what is the angles here? You can say this is negative pi over 2 to where? To the pi over 2, right? So you kind of swim like this way, right? So, okay, so then this one's here we say is what? Is swing like this way, so it's from negative pi over 2 to the pi over 2, see here. And then in here, this is pretty cool. This is r squared, this r's here. So you can use u sub, right? So you can use u sub. So you can say u is equal to what? R squared. Then you use u sub, and then we can get this ones here. And also the theta, we can really separate to a, the two things here. You can say this is negative pi over 2 to the pi over 2. Then you can do a d theta here. Then this is z over 2 e to r squared r dr. Okay, so you can separate out because they have the fixed the fixed integration region. So it's the rectangular integration regions, right? So it's fine. So in here, what do we have here? So it's theta pi over 2 to the negative pi over 2 here. And so you can integrate this by the integration. So if you do this integration by part, this one should give you is negative 1/2 e to the negative r squared. Then you substitute 2 and 0. So after you integrate the whole thing, so then this integration, the answer will be pi over 2, 1 minus e to the negative 4. Okay. Right, so it's pretty cool. Okay, so now we're going to do something interesting here. If you still remember correctly, like in the calculus 2, when you talk about the parametric, the equation, we have a lot of those graphs, right? So we have like the roses, cardioids here. So in here, let's try to do number 16 here. We said the region enclosed by both the cardioids are equal to the 1 plus cosine theta and r equal to the 1 minus cosine theta. So I'm going to find the region. So find the area. Like when we in the calculus 2, this type of the problem is quite difficult, right? So we have a heart here, kind of like, don't know, you guys still remember, right? You did that in the, okay? So for this ones here, so if this is r equal to the 1 plus cosine theta, and then if you have 1 minus, you go like the opposite. Oh, okay, so you go the opposite. This is the r equal to the 1 minus cosine theta, right? So then they want us to find the area between here. And in the in the calculus 2, the integration find the area is not an easy one to do. Okay, so now let's see here. How do I write these d's, right? So this region D, if you use the plural, okay, so what is the, the will be what? Okay, so in here, instead of looking all 4 of them, okay, so I'm only going to look at this one, this part, okay? So this part, okay, take a look. R is from where to where? From R is from 0 to 1 minus cosine theta. Because if I can find this part, I can times 4 because this is symmetric. Now, what is the theta here? Theta is from here, go boom to here, right? So theta is from 0 to what? To the pi over 2 here. Okay, so now the total area will be 4 times the area of these, right? Now we also learned the double integral. If I let the f of xy to be 1, I can find the areas, right? So now in here, okay, I set equal to 1, but don't forget I have what here? I have a Jacobians here, right? So it's the R is my Jacobian. And then remember here, we want to integrate it out with variable. So we do the dr d theta, right? So, okay, so now in here, the R is from 0 in the 1 minus cosine theta. Then let's take a look at the theta, right? So theta is equal to 0 over pi over 2, then times 4 here. Okay, so now this one's here. Okay, so when you integrate the R out, it says R squared over 2. So you have a 2 here, 0 pi over 2. Then you have the R squared. Then you put a 1 minus cosine theta, and then d theta here, right? Okay, so now you will have 0 pi over 2. Then the 1 minus cosine theta. So it's 1 minus what? 2 cosine theta plus cosine square theta d theta, right? So this one is easy to integrate. And how about this one here? So this is cosine square. So remember, then we use what? We use the half angle formula again, right? Change it to the 1 plus cosine 2 theta here, right? So after you integrate this one, so we get the answers here, which is equal to the 3 pi over 2 minus 4 here. Okay, so for this one here, you find 1, you times 4 here. Okay, so the last problem here we want to do, let's take a look. This one's here. Okay, I want to find, find the volume of the given solid here. Okay, so the number 26 here, they say the paraboloid, right, is z equal to the 6 minus x squared y squared, and z is equal to the 2x squared plus 2y. So we want to find the solid bounded by these two, right? So if bounded by these two, that means what? That means these two, they what? They have to what? They intersect, right? So that means I have this 6 minus x squared minus y squared will be equal to what? Be equal to the 2x squared plus 2y squares here. So now I have like, so here I have, this is x, y, so I can have 3x squared plus 3y squared equal to 6. Oh, I got x squared plus y squared equal to what? Equal to 2 here. All right. So now the volumes, right? So the volumes will just be, so this is where is their integration region. So the volume will just be, you integrate over this integration region, x plus y squared less than equal to 2, and bounded by these two, right? So that means if you use the top surface and the volume minus you use the bottom, right? Okay, so now you have the D what? The area dA here, okay? So now if you combine this one is a little bit, so this is x squared plus y squared less than 2. So this one will be 6 minus 3 x squared plus y squared dA, right? Okay, so now I know if I use the Cartesian, this one probably will be very difficult. So I'm using the polars here. Okay, so this is 6 minus x squared plus y squared is what is r squared, right? So it's 6 minus 3r squared. And don't forget what I need to have here, Jacobians here, right? Okay, now I need to decide I'm going to do the dr d theta, right? So the dr d theta. And then you take a look, this is our integration region. It's x squared plus y squared equals to the 2. So what is this integration region? It's a what? It's a circle. And what is my radius? Square root of the 2, right? So the r going to be from where to where? 0 to the square root of the 2. And this is the circle, right? So what is my theta here? Is 0 to what? Is 2 pi here. Then, as you can see, this one turns out to be a super easy things, right? So this will be the 0 to pi, and then this one will just be the 6 to the r square. And so this is r cubed. So this is plus. So the 3 to the, okay, so here this is 3 to the 4th r fourth here, right? 3 to the 4th r fourth, and then I have a 0 square root of the 2. Then I have a d theta. D theta is nothing to the thetas here, right? So my answers here finally, if you carry that out, will be equal to the 6 pi. So pretty cool, huh? Okay, that's it. So we did several problems here. So basically, so yes, you can see the polar coordinates play a very like the important role to simplify your integrations, right? Like for here, how do I find the volume bounded by these two solid in the, in the R3? And so we know if I change it to the polar, and then the integration makes it super easy. And then here, this is what we talk about, the parametric equations, and we learned, in the calculus 2, if you want to use a parametric function to integrate, that would pretty tough layers, right? All right, so then also the other ones here is how do you find, what is the integration region by given the integrals here. All right, that's it. And hope all the problem we did here can help you, to finish this assignment. And also it's a good practice to try to practice the polar coordinates. All right, that's it. And have a good day. And let's take a look at the next assignment worksheets here in our next videos. All right, okay, bye.